So, welcome back to Lab 8, and here is where we ended. We're trying to see whether there is an effect of family therapy on weight gain of individuals with anorexia. And the source is Everett et al. In 1994, so this is real data. And we can see how there is a slight increase in the weight comparing before and after. And I told you, that to be careful with this particular piece of the code. You can use it if you want. In that case, you can put a plus here. And because we're now seeing when you let R first pick the scale, the graph will always show up. And then you can put plus here and control this. Maybe you don't want to start at 0, just to magnify the difference a little bit between the two, so you can play around with that. So here I'm making it go from 50 to 115. And when you do that, you can see how it gets a little bit amplified, the difference here. It's easier to see the difference in the bars. So you can do that as kind of a trick if you want. Not obligated at all to do something like this. The other thing that you can do, again, if you prefer to use the standard error instead, you can do that by doing the square root of 17 in each one of them. But again, not required. Standard deviation is fine for plots. Right, so here is the difference between them. And because standard errors are smaller, we can even get away, I think, if we do 50 to 100. And we can see, we can display the difference a little bit better. All right, so if you want to flip before and after here, because it doesn't make sense that, it makes more sense that before it comes before after. And R will put by default whatever is first on your data set. I think it's alphabetical order. It's not even what comes before, because before comes before. So R by default will put the level of your factor variable that in alphabetical order here. So you can play around with that by using the function scale x discrete. Note that I'm adding a plus, and I do scale x discrete in limits, and then I say go before and then after. If you do that, then you can switch things around. Of course, you won't use before and after for every single data set. It will depend on how your levels are called. For example, if your levels were called condition 1, condition 2, then you would have condition 1, condition 2. Okay? In order to order this thing. So the descriptive statistics shows what to us? That there is promise here, right? That there is an increase in weight with treatment. Now, what the descriptive statistics cannot tell us, and that's why we're not done, is whether the difference in weight observed before and after treatment is likely to happen due to chance alone. I'm going to say this one more time because I think it's so important. If I were to run this experiment 1,000 times, meaning I'll sample 17 girls, 17 anorexic girls, then measure their weight before family therapy. They'll go through family therapy, and then I'll measure their weight after. Even if family therapy had no effect, we would not expect a 0 change in weight every time. Sample again, sample again, sample again. Even if family therapy is horrible, does nothing, does 0, like placebo, the difference between weight before and weight after would not be 0 all the time, even though that would be the true value of the effect of treatment, the true difference in weight in the population. Every time I sample and subject these girls to treatment, you would get something that fluctuates around 0. We need to know what's the expected fluctuation under the hypothesis that we're sampling and subjecting the sample to a treatment that is ineffective, that would thus predict a mean difference of 0, right? So what hypothesis tests allow us to say is what the probability is of observing this magnitude of difference here, right? This difference. What's the probability of observing this difference here from 85 pounds all the way up to 90 something pounds if treatment has no effect? If the probability of observing this just by chance is very small, then we say maybe we should reject the null, that the difference is 0, right? So let's set up the hypothesis. That's why we do this. That's why we do hypothesis tests. So we need to first and foremost define the hypothesis explicitly. So the mean difference equals 0 is the null hypothesis, and the alternative is that the mean difference is different from 0. I'm not saying even that it is greater than 0, because who knows, family therapy for various reasons could actually have a detrimental effect in weight gain. It might not be just placebo, it might mess things up. So we can expect differences in both directions, so we want to set our rejection areas both ways, just in case family therapy turns out to have a negative effect on weight of girls with anorexia. So what's the general code this time? So this time we have a response variable and an explanatory variable. So we need to set this up. So the DV comes first, and then we have this squiggle, and the IV goes after. So the DV in this case is weight, and the IV is treatment, with 2 levels, before and after. Then we need to bring in the name of the data set, which is FT. Then we need to tell it if we want 2-sided, less than or greater than type of hypothesis, 1 tail or 2 tail, and if it's 1 tail, if it's less or greater. And this time we want it 2-sided. We need to give it what the null hypothesis value is. Mean diff for the null hypothesis is 0. We want a paired t-test, so we need to set the parameter paired to true. It could be true or false. In this case, it's true because our means are dependent. And we need to set up our confidence level, which in this case is 0.95, because we're setting up 2 rejection areas, one in one side of the distribution and one in the other side of the distribution. So we want these boundaries, the boundaries of our confidence interval, to set apart the 2 rejection areas. That's why we want the 95 in the middle. All right. So if we run this, and this time we just need to run it 1 time because it's 2-sided, so it brings in the appropriate confidence interval, we can see that the effect of family therapy is to increase the weight somewhere between 3.6 and 11 pounds, more or less, with 90% confidence. We can say that the expected weight gain, because this is positive, is between 3.6 all the way to 11. Right? And we're thinking positive is weight gain because we set up the difference between the differences after minus before. So the 0 is not contained here, which means, quick and dirty way of testing hypothesis, that the difference, finding this difference between 3 and 10 is unlikely under the null. And the p-value for observing the mean difference of 7.26 is just 0.0007, right? So very, very small chance of observing the mean difference 7.26 under the null hypothesis. So what's the decision? Reject the null. What's the interpretation? Data provides evidence that family therapy is effective in promoting weight gain. There was a statistically significant difference in the patient's weight gain before and after therapy. The probability of observing this difference if therapy had no effect is only 0.007. You don't even need these many numbers. The average weight difference can be expected to be between 3.6 and 10.95 pounds with 95% confidence. Thus, even the most conservative estimate of the effect of therapy it can be considered meaningful. Like 3.6 pounds is not nothing, right? The effect could be from small to somewhat moderate for the amount of time that therapy went on. So again, important for us here is that 0 is not within the confidence interval. But the confidence interval is kind of wide. People can gain between 3.5 and 10.9. It would be nice to run this on a larger sample to get a more precise expectation of weight gain with family therapy. All right, now we move on to the next, to a question that's related to this. What could be another explanation for these results that's not the effect of family therapy? And how could you rule out that other possibility? So if you think about it, we have a design that got girls with anorexia, measured their weight before therapy. They went through therapy. It also time passes, right? And then they finish therapy, we measure again. So two things are going on at the same time. The passage of time and therapy. So without a control group, we cannot guarantee that the effect that we saw is not an effect that has to do with the kind of the natural evolution of the disease. Maybe the girls are getting older. Of course, it's not enough time for that kind of thing to happen, but the passage of time in and of itself could be a reason for the observed effect. Potentially even more likely, the impression, the knowledge that you're being treated could result in a placebo effect that has nothing to do with family therapy, but it has to do with the person thinking that they're being treated. So a placebo effect cannot be ruled out either without a control group that actually exposes the person to some kind of sham treatment that is not really effective, but could provide participants with that impression that they are being cared for, to distinguish the effect of placebo from the effect of the family therapy in itself. So two possibilities: passage of time, control group that we just measure the weight again after the same time that we measured the weight prior and after therapy. So that could account for passage of time. If you want placebo, you need to introduce some kind of sham treatment to compare. All right? But the statistics does tell us that the change in weight would not have been observed just by chance alone. Something about the passage of time, the treatment itself, or placebo is generating that effect. And that would need to be disentangled with a more sophisticated design. All right? We'll come back for a third guided activity problem, and we'll conclude our lab for this week. See you then. Bye-bye.